All right, so we are now going to walk through the steps of conducting a t-test for two sample means. And as with the last lecture, in this first example I'm going to go through here, I'm going to talk through the different steps, introduce you to, a new equation for calculating a t-statistic, and then after that I'll go through another quicker example where I'll just do each of the steps with less explanation. So here I'll say, let's go back to that example and say we want to test whether male and female police officers use the same amount of force. We're going to say we take a sample of 33 male officers. And a sample of 31 female police officers. And our goal here is to use these two samples to try to determine whether male officers and female officers in general, so outside of our sample, whether in general they use the same amount of force. So I'm going to write out the statistics for each of these two samples. And I'll say for this test we're going to use an alpha level of 0.05. Alright, so we'll say in sample 1 here, we know that our n for this sample is 33. So n is just the total number of cases. I'm just rewriting all of this in one spot. We're going to say that in this sample, we have a sample mean of 6.2 uses of force. So I'll also call it incidents. So 6.2 incidents of force. And we can make up whatever time frame we want for this. As usual, these numbers are made up by me. So we can say this can be an average of 6.2 incidents in the last week. And we have a standard deviation of 1.1 incidents. So again, this is what you get if you were to just take a sample and then you could calculate the mean for that sample and calculate the standard deviation for that sample. So looking at sample number 2, which is our female officer sample, we have an N of 31, so 31 female officers in the sample. We have a sample mean in this sample of 5.8, and a sample standard deviation in this sample of 0.9. So the question is, we can see that there is a difference between these two numbers. So the male sample has slightly more use of force incidents than the female sample. But the question is this a meaningful difference? In other words, can we be sure that this difference that we're seeing didn't happen just by chance? And even though they really use the same amount of force, it's not that, we just happen to pick a couple of male officers who use more force than average, and we just happen to pick a couple of female officers who use less force than average. And so what we're going to be doing with this hypothesis test is trying to figure out how likely is it that we would have seen a difference as big as this one if male and female officers really do use the same level of force. And since we're going to be looking at differences, I'm going to write out the difference now. And this is going to be the number that we're really interested in here. So our x bar 1 minus x bar 2, or our difference in sample means. And this will be 6.2 minus 5.8, which gives us a difference of 0.4. All right, so this is the setup for the problem. Now we're going to go through our steps for conducting a hypothesis test. And step 1 is going to be to write hypotheses. And I think the nice thing about hypothesis testing, which again is pretty much what we're doing for the rest of the semester, is that once you get the hang of it, the steps that you follow don't change. The only thing that'll change will be what the hypotheses look like, what the test statistic looks like, and how you calculate it. But the logic and all the other ideas behind it are going to be pretty much the same. So the hypotheses for a two-mean t-test are always going to be written in the same way. And this should look like what I put on the slide before. Your null hypothesis is always going to be that there is no difference between your population means. So how we would interpret this is that the null hypothesis is that in the population, so among police officers as a whole, all the police officers there are out there, the sample mean for male police officers is equal to the sample mean for female police officers. And we can write this as saying that if you were to subtract one for the other, it would be equal to 0. So there is no difference between them. Male and female police officers both use the same amount of force in the population. And so if we reject our null hypothesis, we'd have evidence that that wasn't the case, and that really there was some difference in the amount of force used by male and female police officers. So our alternative hypothesis, which is, as usual, the opposite of our null hypothesis, is going to be that there's some difference between these two population means. So either male police officers use more force or female police officers use more force. We're not saying which direction it would go here. We're just saying that there's some difference between them in the population. And so that would be our alternative hypothesis. And as before, we're going to be looking at our samples as evidence to see whether we have reason to reject this null hypothesis and say this isn't true, or whether we don't have enough evidence to say that. And for this example, we can also, you can write these out if you want to just keep track of who you're looking at more. We could also write this out as saying U of M minus U for F, so for male and female police officers is equal to 0, or that it's not equal to 0. And so this is just something that you can do if you want to be able to keep track of your different means better. I don't really care, if you write this out in the homework, whether you say mean 1 and mean 2, or you say mean for male officers, mean for female officers, as long as it has the same structure and you're saying that, the difference in population means in the groups is equal to 0 and not equal to 0. All right, so that's it for step 1 of writing hypotheses. We're saying that either the difference in the population is equal to 0 or it's not. Step 2 is going to be to find a test statistic. And this is a t-test, which means that our test statistic is going to be a t-statistic. And next week we'll meet a hypothesis test where that's not the case. All right, but starting with this one. So we're going to be looking for a t-statistic. Statistic. All right, so looking for a t-statistic. And for a 2-sample t-test, we're going to be using a t-statistic that you find with the following formula. All right, so what we have here is our first sample mean, our second sample mean, x bar 2, and then this big chunky thing on the denominator, which is the standard error for the sampling distribution. And here, when we were only looking at one mean, let me just adjust this thing. So when we were only looking at one mean, it was just S sub x bar. Here we're going to be looking at that distribution of differences in means. So what we have in the bottom here is S sub x bar minus 1 minus x bar 2. So again, we're going to call this the standard error for the sampling distribution. And for this particular hypothesis test, the standard error for this sampling distribution is kind of a pain in the butt to calculate. So I'm not going to have you guys do it here. So last week you had to calculate this number that went on the bottom of the t-statistic calculation. This week, you don't have to calculate it, and I'm just going to give it to you. So with any of these problems, I'll be giving it to you. So in this particular case, the standard error for the sampling distribution, and here I'll just use M and F just to denote that that's what we're looking at. The standard error for our sampling distribution for the difference in means is going to be equal to 0.252. So when we start plugging things into this equation, that's what you'll be able to plug in. All right, so I'm going to go over to this next page here and start actually plugging this stuff in. Just so you can follow what I'm doing, I'm going to rewrite the equation here, but this will be the same exact equation as I had on the last slide. So we have our t-statistic for our difference in means. It's going to be equal to mean 1 minus mean 2 over the standard error for our sampling distribution for the difference in means. And now we can plug stuff in. So we have sample mean 1 here, which we said was equal to 6.2 incidents. Sample mean 2 we said was equal to 5.8 incidents. And then we have our standard error, which, as I said before, I'm going to give to you because it's just super annoying to calculate from the sample statistics, is 0.252. But if you are curious, which I'm sure you're all incredibly curious about this, you do calculate that standard error from your mean and sample standard deviations, similar to how you would in a one sample t-test. It's just that because you have 2 samples to work with and 2 means and 2 standard deviations, they have to be combined in a way that just involves a bit more math. So we're not going to do it. But that is where that number comes from. All right, so now we have plugged in our stuff. We can just do the math out here to get our answer. So anytime you see this, just as a reminder, make sure you do the math that's on the top of the equation, so in the numerator, before you divide. Otherwise, you'll get answers that are wonky. So if we do this out, we get 0.4 over 0.252, and that comes out to a value of 1.59. So that there is our test statistic. And so, as with any test statistic, what this tells us is where our sample values would fall on our sampling distribution. So the sampling distribution we're looking at is the same one that I wrote out on that other page there. So this is the sampling distribution for the difference in population means, or sorry, the difference in sample means, with our overall mean being that there is a difference of 0 in between the population means. So we're going to say this is based on our null hypothesis that there's no difference between the use of force by males and by females in the population. So no difference is a difference of 0, and that is our most likely sample value. So here we're going to say on the x-axis we have our difference in sample means, and on the our mean of the sampling distribution here is 0, where again 0 means that there is no difference in between the sample means. And now what we're going to be doing is, instead of writing this in terms of the raw numbers, we're going to convert this to t-statistics. So this is the same idea as standardizing any other sampling distribution, where instead of having the difference in sample means at the bottom, we have a t-statistic. So let me just fill the rest of this in here. So this is our difference in sample means, and if we were to plot our actual difference in sample means on this, we had a difference in sample means of 0.4. So this, and I'm squished everything together a little bit too much, but this line here would refer to our actual difference in sample means. So when we found our sample means, we subtracted them, we got a value of 0.4, and we plotted it on our sampling distribution for the difference in sample means. Now we're going to standardize everything and just turn it into a regular old t-distribution with t-statistics on the x-axis. So same idea as converting a normal distribution into a standard normal distribution with z-scores. Our only difference is that here we have t-distributions, and so we have t-statistics on the bottom here. And so our mean stays the same, because here it's already 0. But now we can plot our sample in terms of this test statistic that we found. And so our test statistic lands at 1.59. So this is saying that we are 1.59 t-scores away from our mean of the distribution of 0. So you can interpret this again in the same way that you would interpret a z-score. It's how far away are you from the mean of the distribution. So we're looking at the same thing here. The only difference is that instead of looking at this raw difference that we have of 0.4, we're converting it to a t-score. And so with this, our next step is going to be deciding whether to reject the null hypothesis. And if you remember, that question is going to be answered by looking at whether this score that we found is in the really unlikely range on the outside here, or the likely range on the inside. And unfortunately, my drawings are horribly not to scale, so you really can't just eyeball it. But the question is whether this line would actually be in the middle here or whether it would be out towards the sides. But I kind of wish I hadn't drawn that there because it makes it look like you can tell from here. But we can't. All right, so our next step then is going to be to use the p-value that we get from this sampling distribution to decide whether to reject the null hypothesis. And I'll just say, please ignore the shading for now. Downside to writing in pen and not on a chalkboard is my mistakes are forever. All right. So our last step here is to decide whether to reject the null hypothesis. And just to clarify my own editorializing, this isn't a mistake in terms of being the wrong thing to do. It's just no, we don't actually have information about which side of the line this would be on right now. So this should just be a distribution without any shading. All right, so as with the last t-test that we did, I'm going to tell you what p-value corresponds to your t-statistic. And this is because the calculation of this, again, is not something that's really worth ever learning to do by hand. So we're just going to say that for a t-statistic of t equals 1.59, p is equal to 0.1178. So that's something that, a computer would crunch these numbers. It would tell you, it could tell you the t-statistic, it would also tell you the p-value that goes along with that t-statistic. And again, a p-value tells you the probability that you'd get a sample statistic as extreme or more extreme than your sample statistic. And that probability is based on the amount of area that is further away from the mean than your actual sample statistic on the sampling distribution. So we would interpret this p-value of 0.1178 like this. We would say if the population means truly were the same, so if the null hypothesis were true, we would see a difference in sample means as big as 0.4 or bigger only 11.78% of the time. So if the null hypothesis were true, we would see a difference in sample means as big as 0.4 or bigger 11.78% of the time, just by chance. And again, thinking about our specific example, we'd be saying that if male and female police officers really did use exactly the same amount of force in the population, we would see a difference in sample means as big as 0.4 or bigger 11.78% of the time, just by chance. And I'll add just by chance here. So now we're going to decide whether to reject our null hypothesis. And our rules for making this decision are the same. If P is less than alpha, we reject our null hypothesis. If P is greater than alpha, we fail to reject our null hypothesis. So in this particular case, P is equal to 0.1178, and we said that our alpha level was going to be 0.05. So we have 0.1178, which is our p-value, and as it turns out, it is larger than our alpha value. So the chances that you'd see a difference in sample means as big as the ones that we have here just by chance, assuming that the population means were really the same, those chances are more than what we consider our threshold for saying that it's too unlikely. So in other words, we have an 11.78% chance, and we're saying it would have to be a 5% chance or less for us to consider it too unlikely. So because of this, we fail to reject the null hypothesis. And we would say it's still pretty likely. There is a full, almost 12% chance that if the population means were really the same, we would have gotten the samples that we did, or samples that are even further apart, or have means that are even further apart. So because of this, we don't have enough evidence to say that male and female police officers use different amounts of force. The sample means are too similar to each other for us to say that they didn't come from the same population. So we fail to reject our null hypothesis. And so that means that if you were to actually draw this at the right time, it would look like what I have here, where we have our zones where we would reject HO, and we have our zone in the middle where we fail to reject HO, and our sample here is in the zone where we fail to reject. So now pay attention to my shading. So let me make sure it's on there. So that's what our p-value is telling us. It's telling us that our sample mean is in this zone where we do not reject the null hypothesis. So again, the full takeaway from this example here is that based on those two sample means we have, with a mean of 6.2 and a mean of 5.8, we would say that they're too similar to each other to give us any evidence that male and female police officers don't use the same level of force in the population.